and hello everyone. So I guess you saw my name, and Claudio Contardo and Mathieu Grzon are the other collaborators for this work, both professors at Université and UQAM University. So the topic of this presentation is going to be talking about the set covering problem and doing a bit of a theoretical study of the problems through its polytope, and trying to see what we can say about facets for this polytope, and also how tilting inequalities for the problem can lead to creating facets for the polytope. So the content of this presentation is going to be the following. I'm going to start with a brief introduction on what is the set covering problem and some mathematical objects that will be used during the presentation. Then I'm going to dive a bit on the subject of the inequalities, the facets, and I'm going to introduce the main mathematical object of the presentation, which is going to be the tilting vectors. The next section is going to be about how to use those tilting vectors in order to tilt inequalities for the set covering problem. And finally, I'm going to talk about how to, a bit more about computations, how to take advantage of not tilting general inequalities, but tilting sparse inequalities in order to get those tilting computation done much more efficiently and lose less computing time on those. So let us start with the set covering problem. So the input in the set covering problem are pretty simple. There is a set of elements that are given that are going to be used to cover the other inputs, which are going to be the subsets. So a subset, for example, in this representation, S1 is connected to E1 and E2, and it is because the subset S1 is actually the subset E1, E2. And so what we want to do, the goal of the set covering problem is to select some elements from the E1, E2, E3, E4, and actually try to minimize the number of selected elements. And those selected elements are going to form a cover if each subset contains at least one of the selected elements. So just for the purpose of the presentation, I'm going to use this example a lot, but I'm going to change a bit the layout so it's a bit more readable. So trust me, it's exactly the same as before, but just changing a bit the position of the nodes. Okay, so we want to study this problem through its polytope. So when we have, for example, a very small example here, we usually, when we model this problem, we are going to use one variable for each element, just a binary variable deciding whether or not the element is taken inside of the cover. And so the solution set is just the set of binary vectors that are going to represent the cover. So for example, in this small element, you're allowed to choose E1, E2, or both, but you're not allowed to choose none of them because then the only subset S1 is not covered. And so if we have only two variables, we can represent this in two dimensions. And this is the three allowed binary vectors. And the set covering polytope is just the convex envelope of all those binary vectors. So in this case, it's just the triangle over there. All right, so another object that is going to be very useful for this presentation is going to be the cover hypograph. So the goal of the cover hypograph is just to try to get a representation of all the interesting solution of the problems. So we have a lot of covers. They are all solutions of the problem. In the set covering, we want the one with the minimal size, but the cover hypograph described a bit more than that. It described all of the minimal covers, but inclusion-wise. So just the covers that don't have, from which you cannot remove elements without breaking the fact that they are covers. And so to represent all of those covers, we use a hypergraph. The hypergraph contains one node for each of the elements. And then each edge or hyperedge is going to represent one of the minimal covers. So for example, the cover E1, E2, which in this covers all of the subsets, is going to be represented with this edge. and the same for E1, E3, and E1, E4. And the last minimal cover in this example is going to be E2, E3, E4, which in this case is actually going to be represented by a true hyperhedge because this cover is of size 3. Okay, so more about inequalities and facets. So what kind of inequalities are we going to study in this problem? Actually, it is known that for the set covering problem, the only inequalities that are relevant to study, which means that they can be facets, so non-redundant inequalities, are going to be of this form. So alpha x greater or equal than gamma alpha, with alpha positive coefficients, and always this greater or equal sign because the other inequalities can never be facets of the polyhedron. And what is gamma alpha? It is just the best right-hand side, I would say. It's, if you take a right-hand side that is too high, then you're cutting too many vertices and the inequality is not valid for the polytope that you consider. If you take it too low, then the inequality is shifted too large and it's not even touching the polyhedron, so it doesn't have any chance of being a facet. So we just consider inequalities that are actually valid and touching the polyhedron, and there is only one right-hand side for that. So among those inequalities, we're specifically interested into facets. So what is a facet? A facet is a valid inequality that is going to touch the polyhedron into many independent points. So for example, and many in this case is just a number of independent points that is equal to the dimension of the polytope. So in the earlier example, if we take this inequality, it touches this polytope of dimension 2 only in one point, so it is not a facet, but this one touches in at least 2 independent points, so it is a facet of the polyhedron. And why are we interested so much about facets for the polyhedron? It's just that in general, for mixed integral linear program, we tend to use those a lot to solve those kinds of programs a lot in operational research. And the main way to do that is branch and bound or branch and cut most of the time. And the cutting part in the branch and cut is generating valid inequalities for the polyhedron that you consider. And it is well known that if the inequality is a facet, it has more chance to improve the method, more to give better results than if you use inequalities that don't have those structural properties for the polyhedron. So that's why we are interested in trying to get inequalities that are at least closer to facets or facets if possible. So because a facet is just a valid inequality that touches the polyhedron in many points, we are going to be interested in the set of contact points of the inequality with the polyhedron. So I'm going to denote this set just x equal alpha because it's the set of binary vectors that represent a cover, so a valid solution, and that are on the hyperplane of the inequalities so it satisfies the inequality to equality. And we can represent this set of contact points with another hypergraph. Actually, it's just a sub hypergraph of the one we had before, because all of the contact points are going to be minimal covers. And so, for example, if we take this valid inequality, which says that you need to choose at least 2 elements in order to have a solution for this instance, and it's true, like the only possible covers have at least 2 elements, then the covers that actually satisfy this to equality are the covers of size exactly 2, and we can represent that with the hypergraph we had before, just removing the cover size 3 in the hypergraph. So this smaller hypergraph is going to represent the set of contact points of the inequality with the polyhedron. All right, so that's finished for the introduction. And we are going to now present the main mathematical object that we introduce is the tilting vector. So a definition. So what is a tilting vector beta for an inequality alpha x greater or equal than gamma alpha? Then it's just a vector that satisfies beta x equals 0 for every contact point. So it means that beta is just an assignment of coefficient to the nodes of to the elements of the problem. and we want that the sum of the coefficients on a cover that is a contact point is equal to 0. So we want sum of the elements to be equal to 0. So let's make an example with the earlier example. So remember, all of the edges here represent contact points. So let us try to create a tilting vector. So maybe put a 1 onto the first element. Then we know that, for example, for this cover, so for this contact point, we want the sum of the coefficient to be 0. So we have to put a -1 here, and all of the other constraints are going to enforce us to get -1 on all of the other elements. So that's just an example, but why are we interested in tilting vectors? Well, the rest of the presentation is going to be about how to use them to tilt inequalities, but also the other part of the paper that is related to this presentation, I will not have time to present, is how to use tilting vectors to kind of characterize which inequalities are facet or not facet. And the main theorem, or the first theorem that comes on that subject is that if you have an inequality, it is a facet if and only if the only tilting vector has only 0 coefficients, or only 0 coefficients. So in this case, it means that, for example, these inequalities for which we just created a tilting vectors because it satisfies all the constraints in the definition, it is non-null. So this inequality is not a facet of the instance that we presented before. All right, so how to use those tilting vectors to tilt inequalities. So first, what do I mean by tilting inequalities? So when we have an initial inequality here, the tilting of any tilting of this inequality is going to be another inequality with where we have modified the coefficient by using a tilting vector. And so why not change the coefficient arbitrarily? Why use tilting vectors? It is because it actually preserves the set of contact points. Because if you have a contact point, which means that it satisfies alpha x equal gamma alpha, and it also means by definition of the tilting vector that beta x equals 0. Then, if you look at this, you also get an equality to gamma alpha, and this means that it's also a contact point of the inequality. So it means that a tilting of an inequality is kind of a rotation of this inequality around its set of contact points. So here, just graphically, we have a polyhedron and an inequality in blue, and we can see that tilting this inequality is just rotating it around its set of contact points, and depending on the epsilon we choose, we get more or less rotation. And so the really interesting part is that if you choose the proper epsilon, then you can have an inequality that kind of hugs more the polyhedron than the one you had before. And you kind of, well, mathematically, you increase the dimension of the face that this new inequality is creating on the polyhedron. And so the idea about tilting is going to try to tilt inequalities again and again to increase the dimension. And if you do that continuously until you have no more tilting vectors available, then you obtain a facet of the polyhedron. But the main thing that you have to know how to do now is how to choose the epsilon that will give you the proper tilting. All right, so let's describe a simple algorithm that can do that for you. So if you have a polyhedron, so I cannot represent any interesting set covering polyhedron, so I'm just going to use this polyhedron and an inequality, and you're given also a tilting vector. So how to find the epsilon that will enable you to get the inequality that hugs the space? So first you can start by trying epsilon way too large. So in that case, you know that it's not going to be valid for the polyhedron because you choose epsilon too large. There's a simple way in set covering to decide an epsilon that is too large. It's very easy to do. And then the next step is going to optimize in the polyhedron for which you want to tilt along the direction alpha plus epsilon 1 beta. So that's just solving a set covering problem. If this polyhedron is a set covering, it's just solving a set covering problem with the objective function alpha plus epsilon 1 beta. So then you obtain a point that is going to maximize this function. And you're going to change the epsilon to get the inequality to pass through this new point. And you're going to continue the optimization and changing the epsilon until when you optimize, you don't get a better point than the one you just created before. And then you know that your inequality is then valid for the polyhedron. And so you have an inequality that is valid for the polyhedron. And the last point that you computed is actually independent from the other one. It's a contact point of the inequality, and it's independent from the other ones. So you get a valid inequality that has a larger number of independent contact points. So you achieve your goal of creating a better inequality. All right. So the thing you have to remember, the main step of the computation here is not going to compute. It's not going to be to compute the epsilon 3 that is passing through x2. It's going to be the optimization step, optimizing on the set covering polyhedron with any of the objective functions. And so we are going to see how to do this computation faster when you have an inequality that has a lot of null coefficients. So why null coefficients are advantageous? It's because if you have a set covering problem with a random objective function and some of the coefficients in the objective function are equal to 0, then, well, let's look at what happens. So let's assume that there is a 0 in the objective function for E1. You want to cover all of the subsets, and adding E1 to the cover is not going to cost you anything in terms of objective function. So you can decide to add it to the cover. So you know that for example, in here, S1, S2, and S3 are going to be covered whatever because you already added E1 without any increase in the objective function. So what you can do is just remove E1 and remove all of the subset that it covers. And then you obtain a smaller problem to solve. So if you have many 0 coefficients in your problem, then you can remove most of the elements and you can remove most of the subsets, and you have a very small problem to solve. So solving that is much easier than solving for example, the original problem with one for every element. All right. And so we saw that for tilting, the main computation was to solve a set covering problem with the objective function alpha plus epsilon beta. And so if we have an inequality alpha which is sparse, if we can get a tilting vector beta that is, well, whose non-zero elements are included in the one of alpha, then we can have alpha plus epsilon beta that is going to be sparse. And then we can have a faster computation through the shrinking of the instance that I told you before. And also, once you get the tilting, if you want to keep tilting the inequality, you will start again from alpha plus epsilon beta, which is still as sparse as the alpha you had before. So if you can keep going in this way, you can tilt a lot the inequalities with shorter computations. The only thing that you have to require is that, well, the non-zero elements of beta are included in the one of alpha. So the question you may ask is there any such vector? If there is one, is there many? Can you do a lot of tilting with it? Or it's just like you're going to get one and then you have to do all of the rest and it's not very interesting. And what we were able to show is that actually there is when you consider all of the tilting vectors for an inequality, you have two subfamily, I would say. There is here the tilting vectors that do have their support included in the one of alpha. And there is only a few other ones, actually, and they have a very specific form. They have the following form. They are equal to alpha minus gamma alpha, and this vector is just a unit vector with only a lot of zeros and only 1, 1. And actually, so what it look like is just the vector alpha with always these 0 components and all these non-zero components here. And we add just one new coefficient that is going to be minus gamma alpha. to a space where there was a zero component before. And so what this theorem shows is that you can start by using all of the tilting vectors that have their support included in the one of alpha, and then your tilting computations are much faster. And then when you have exhausted all of them, you get this last family of tilting vectors that have actually one more coefficient than alpha. So it means that every time that you tilt, you're going to increase the support of your inequality by 1. And the good thing about those tilting vectors is that they do not require, as the other one, they do not require an iterative process to compute the tilting. They can be solved in only one set covering resolution. So in the end, you have a fast computation for all of those where the support is small. And then you have this last family where the computation of the tilting is a bit faster, and you only increase the support by 1 every time. So you can stop a bit like when it gets a bit too hard or. Yeah. And so so that's how you can improve your computation for sparse inequalities. As a conclusion, well, tilting vectors are very useful. They can be used, as I showed, like for tilting inequalities, but also there is, if you're interested in the paper, there is a whole part of the paper trying to characterize which inequalities can be facets of the set covering polyhedron. And this can be done a lot using tilting vectors because they, as I showed before, knowing whether or not there is a non-zero tilting vector kind of characterizes whether or not an inequality is a facet for the polyhedron. All right, thank you for your attention.